Alright, let's go. Number 10. The Casimir Anomaly. In 1996, Umar Mohideen and Anushree Roy at the University of California, Riverside were not trying to break quantum electrodynamics. They were trying to confirm it. Their goal was a precise, clean verification of the Casimir effect, the measurable attraction between two uncharged metal plates suspended in vacuum, caused by quantum fluctuations in the electromagnetic field. Routine calibration work. The kind of thing that fills a paragraph in a textbook. Quantum electrodynamics, the most accurately tested theory in all of science, predicts this force exactly. The math is not ambiguous. At separations above 100 nanometers, the force obeys a clean inverse fourth power law. Every measurement made through the 1970s and 1980s matched. There was no controversy. Then they got to 100 nanometers. And the force didn't match. Mohideen and Roy published in Physical Review Letters in 1998. At nanoscale separations below 100 nanometers, the measured Casimir force deviated from Ked's prediction by up to 15%. Not a rounding error, not an instrumental artifact. A systematic, reproducible deviation. Steve Lamoureux at Los Alamos National Laboratory independently measured the same regime in 1997 and found the same discrepancy. 15% is a universe-sized gap in a theory that usually matches to 11 decimal places. Physicists proposed surface roughness as the culprit, real plates aren't perfectly smooth, and the theory assumes ideal conductors. They built correction models. The correction didn't close the gap. They proposed finite conductivity effects. Real metals aren't perfect conductors. They modeled it. Still off. They proposed temperature corrections to the vacuum fluctuation spectrum. Still off. Ricardo Decca at Indiana University ran a torsion pendulum experiment in 2005, published in Annals of Physics. Specifically designed to eliminate every known systematic. He still found deviations. Each proposed fix closes part of the gap and opens questions about why the fix is needed at all. If the deviation is real, it means quantum electrodynamics, the theory that predicts the magnetic moment of the electron to 11 decimal places, fails at close range. Which means the vacuum at nanoscale distances behaves differently than our best theory says it should. The vacuum. The thing you're made of, between your atoms. What is interacting with those plates that our equations are missing? The universe's quietest experiments tend to produce its loudest questions. Number 9. The Lorentz invariance violation. In 2009, a team led by Julien Granot at the University of Hertfordshire was analyzing data from the Fermi Gamma Ray Space Telescope, which had recorded a gamma-ray burst, GRB 090510, from a galaxy 7.3 billion light-years away. Granot wasn't looking for a crack in spacetime. He was building a light curve model of the burst's emission spectrum. Standard astrophysics bookkeeping. Special relativity requires that the speed of light be constant for all photons regardless of energy. This is Lorentz invariance, the foundational symmetry of Einstein's theory, and by extension all of particle physics. Every measurement ever made on Earth confirms it. It is one of the most well-tested principles in physics. The Fermi data showed that a high-energy photon at 31 GeV, roughly 31 billion electron volts, arrived 0.859 seconds after the burst's lower-energy photons, having traveled 7.3 billion light-years. The arrival delay was small. The implication was not. Granot's team published in Nature in 2009. If the speed of light varies with energy, even by 1 part in 10 to the power of 19, that would violate Lorentz invariance and confirm a prediction of certain quantum gravity models, including loop quantum gravity and some string theoretic approaches, which propose that spacetime itself has a granular structure at the Planck scale of 1.616 times 10 to the minus 35 meters. The delay placed the quantum gravity energy scale at or above 1.2 times the Planck energy. Giovanni Amelino Camiglia at Sapienza University in Rome had predicted exactly this effect in 1998, published in Nature, calling it rainbow gravity. The argument against the delay could be intrinsic to the burst's emission mechanism, not a propagation effect. Photons at different energies might be emitted at slightly different times at the source. Models of burst physics cannot rule this out. The argument for, across dozens of GRBs analyzed by the Fermi team, the delay scales consistently with distance in ways that intrinsic emission timing shouldn't. Tzvi Piran at Hebrew University published a 2015 analysis in Physical Review Letters showing the correlation holds statistically across 35 bursts. If Lorentz invariance is slightly broken at Planck scale energies, then every equation in the standard model, every calculation of how particles interact, decay, or scatter, is an approximation of a deeper theory we haven't found yet. The GPs in your phone works because those equations are exactly right. Exactly. How close to exactly? Symmetry violations tend to compound. Number 8. The Kaon CP violation excess. In 1964, James Cronin and Val Fitch at Princeton University were not hunting for evidence of physics beyond the standard model. They were performing a routine test of CP symmetry, the principle that matter and antimatter behave identically under combined charge parity reversal, using a beam of neutral kaons at Brookhaven National Laboratory. The test was expected to confirm the symmetry. Confirm it, and go home. The standard model predicts that matter and antimatter should be created in equal amounts in the early universe, and should obey the same decay rules. CP violation, the measured asymmetry in kaon decays, was first discovered in 1964 by that same Cronin-Fitch experiment, earning them the 1980 Nobel Prize. The standard model incorporated this violation through a mechanism called the CKM matrix, developed by Makoto Kobayashi and Toshihide Masukawa in 1973, published in Progress of Theoretical Physics. The problem is the magnitude. The standard model's CKM mechanism predicts CP violation in kaon mixing at a level of epsilon circly 2.228 times 10 to the minus 3. The measured value, averaged across experiments at CERN's NA48 experiment and Fermilab's KTV experiment, published jointly in a 2002 review in Physics Reports by Gilman, Kleinknecht, and Rank, is consistent with CKM predictions to within 10%. But that 10% isn't a rounding error. It represents a measured parameter called epsilon prime over epsilon, the direct CP violation ratio in kaon decay to pions, which experiments measured at 1.66 times 10 to the minus 3, while theoretical QCD calculations give a range of 1 to 30 times 10 to the minus 4. The theoretical range is so wide, it renders the prediction nearly unfalsifiable. And unfalsifiable predictions are not predictions. Anton Pitch at the University of Valencia published a thorough review in 2004 in the International Journal of Modern Physics, cataloging every attempt to tighten the theoretical calculation. Lattice QCD approaches reduce the uncertainty, but don't eliminate it. New contributions from penguin diagrams add corrections, but introduce new free parameters. Every refinement needs another refinement behind it. If the standard model cannot precisely predict kaon CP violation, the simplest, most measured CP violating system we have, then our explanation for why the universe contains matter at all is built on arithmetic we cannot fully verify. You exist because matter won slightly over antimatter in the first second after the Big Bang. The calculation that explains that win has a 10% error bar baked in. What is hiding inside that uncertainty? From matter-antimatter asymmetry to the structure of matter itself. Number 7. The proton radius puzzle. Randolph Pohl at the Max Planck Institute of Quantum Optics was not trying to challenge atomic physics in 2010. He was trying to measure the proton more precisely. His team used muonic hydrogen atoms, where the electron is replaced by a muon, a particle 207 times heavier. Because the muon orbits 207 times closer to the nucleus, making it far more sensitive to the proton's charge radius. This was meant to be a precision measurement. A refinement, standard quantum electrodynamics applied to regular electron hydrogen, gives a proton charge radius of 0.8768 femtometers. That is 0,8768 times 10 to the minus 15 meters. This value was measured across decades of electron scattering experiments and confirmed by the Kodada Committee's 2006 global average. It was settled science. Pohl's team used muonic hydrogen spectroscopy and got 0.8409 femtometers, the same proton, a different size. The discrepancy was 4%, or 7.9 standard deviations, an almost impossible statistical accident. Pohl published in Nature in 2010, and then again with refined measurements in Science in 2013, with co-author Aldo Antognini at ETH Zurich. The physics community proposed experimental error in the muon measurement. Ruled out after 3 independent calibrations. Incorrect KED-radiative corrections applied to the muonic system. Physicists including Jean-Philippe Carr at Sorbonne University reviewed every 2-loop and 3-loop correction. Still off. Proton structure effects, polarizability corrections. Carl Carlson at the College of William and Mary published a comprehensive review in Progress in Particle and Nuclear Physics in 2015. The corrections exist, but are far too small to close the gap. The PRAD experiment at Jefferson Laboratory remeasured the electron-based radius in 2019, published in Nature, and found 0.831 femtometers, closer to the muonic value, but still not identical. If the radius genuinely differs between measurement methods, it means quantum electrodynamics treats electrons and muons differently at short distances. The standard model says they should be identical except for mass. If they're not, if there is a new force that couples differently to muons than to electrons, then there is physics below the standard model that only reveals itself when you get close enough to a proton. The proton is inside every atom in your body. Its radius is apparently not a fixed number. The matter below your skin keeps hiding things. Number 6. The neutron lifetime discrepancy. In the early 1990s, 2 groups of physicists were independently trying to measure the same quantity, how long a free neutron lives before decaying into a proton, electron, and antineutrino. This is not exotic physics. It feeds directly into calculations of Big Bang nucleosynthesis, the process that determined how much helium, deuterium, and lithium the early universe made. Getting the neutron lifetime right was essential for understanding why the universe's hydrogen-to-helium ratio is 3:1. Both methods should give the same number. In the bottle method, cold neutrons are stored in a magnetic or material trap and counted as they decay. In the beam method, a neutron beam passes a detector that counts the protons produced by decay. Same particle, same decay, same physics. Bottle experiments give a neutron lifetime of 877.75 seconds, 14 minutes and 37.75 seconds. Beam experiments give 887.7 seconds, 14 minutes and 47.7 seconds. The discrepancy is 8.9 seconds, or roughly 4 standard deviations. It is not closed in 30 years of increasingly precise measurement. Fred Wheatfeld at Tulane University and Jeffrey Green at Oak Ridge National Laboratory published a comprehensive review of the discrepancy in Nuclear Physics A in 2011. They cataloged the proposed explanations. Systematic error in magnetic storage, neutrons lost through trap imperfections inflate the bottle result. Physicists built cleaner traps. The gap remained. Detection efficiency errors in beam experiments. Teams calibrated independently. The gap remained. In 2018, Brooke Russell, Christopher Morris, and colleagues at Los Alamos National Laboratory published a new bottle measurement in Science using a unique ultra-cold neutron storage vessel. Their value, 877.75.28 seconds. The beam result that same year, 887.72.2 seconds, still 8.9 seconds apart. The disturbing explanation is dark matter. If neutrons occasionally decay into dark matter particles, a process called dark decay, proposed by Bartosz Fornal and Benjamin Grinstein at UC San Diego in a 2018 Physical Review Letters paper, the bottle experiment would count fewer neutrons who vanished into undetectable dark particles, while the beam experiment, which counts decay products directly, would only record standard decays. The 1% dark decay branching ratio needed to explain the gap is technically allowed by current constraints. 8 seconds. 1% of decays. Into something we cannot detect. Inside every atom you have ever touched. Dark matter keeps appearing where we don't expect it. Number 5. Modified Newtonian dynamics. In 1983, Mordechai Milgram at the Weizmann Institute of Science in Israel was not trying to invalidate dark matter theory. Dark matter theory barely existed yet. He was trying to explain why galaxy rotation curves were flat, stars at the outer edges of galaxies orbit at the same speed as stars near the center, violating Newtonian gravity's prediction that outer stars should slow down, just as Neptune moves slower than Mercury. Milgram thought he was proposing a minor correction to gravity at low accelerations. A patch. Standard Newtonian dynamics, scaled up to galactic distances with dark matter halos added, predicts galaxy rotation curves by fitting a free parameter, the dark matter distribution, to each galaxy. The fits often work, but they require assuming the dark matter halo has a specific profile that cannot be directly observed. Every galaxy is fitted separately. Milgram's alternative MOND, Modified Newtonian Dynamics, published in 3 papers in the Astrophysical Journal in 1983, uses a single universal constant, a sector 1.2 times 10 to the minus 10 meters per second squared, below which Newton's second law is modified. No free parameters per galaxy. One number. Fixed. MOND correctly predicted the rotation curves of over 150 galaxies without fitting. This was documented by Stacy McGaugh at Case Western Reserve University, Federico Lelli at the European Southern Observatory, and James Schaumbert at the University of Oregon in a landmark 2016 science paper analyzing the SPARC database. When they plotted the radial acceleration relation, centripetal acceleration versus baryonic surface density, every galaxy fell on the same line. Dark matter models scatter. MOND snaps them onto a single curve. McGaugh's team found the residual scatter was only 0.11 dex, consistent with measurement error alone. Dark matter halos, being unobserved and adjustable, should not produce this tight a correlation. They don't have a mechanism that forces them to. The argument against MOND, galaxy clusters in the bullet cluster, show mass offset from visible matter that MOND cannot explain without dark matter. The argument that won't die. Why does a simple formula with one fixed constant correctly predict the behavior of 150 structurally diverse galaxies? That level of predictive accuracy from a wrong theory has no precedent in physics. If MOND is pointing at something real, a modification of inertia or gravity at low accelerations, then every dark matter experiment run for the past 40 years has been searching in the wrong place, looking for a particle that doesn't exist, while the answer was hiding in the acceleration. How many more correct predictions does a theory need before we take it seriously? Gravity keeps misbehaving at scale. Number 4. Dark energy as a fifth force. In 1998, Saul Perlmutter at Lawrence Berkeley National Laboratory and Brian Schmidt at Australian National University were leading competing teams, both trying to measure the deceleration of the universe's expansion using Type 1 supernovae as standard candles. The assumption was that gravity was slowing things down. The goal was to measure by how much. General relativity, with Einstein's original cosmological constant lambda, predicts that a positive vacuum energy density causes accelerating expansion. Einstein added lambda, removed it as a blunder, and then quantum field theory predicted vacuum energy 120 orders of magnitude larger than what would cause observed acceleration. A discrepancy so extreme it is the worst prediction in physics. The cosmological constant was considered dead. Perlmutter and Schmidt both found that distant supernovae were dimmer than they should be. The universe was not decelerating. It was accelerating. They published in the Astrophysical Journal in 1999, earning the 2011 Nobel Prize. Dark energy was born. The problem is that dark energy behaves suspiciously unlike a cosmological constant. Konstantinos Skordas at the University of Nottingham and Tom Zonik at the Czech Academy of Sciences published a 2021 Physical Review Letters paper showing that a relativistic modification of gravity, a tensor vector scalar theory, fits all current cosmological data as well as lambda CDM, without requiring dark energy at all. Eric Linder at Lawrence Berkeley published analysis in Physical Review D in 2005, showing that the dark energy equation of state parameter W, which should equal -1 exactly for a cosmological constant, is measured at W (-1.030.03). That's consistent with -1, but the error bar is large enough to hide a time-varying field. The Dark Energy Survey's 2022 results and the Planck satellite's 2018 full data release both measure W within this range. The James Webb Space Telescope's early data on high redshift galaxy formation suggests structure formed earlier than lambda CDM predicts, a tension that has reached 3.5 sigma. If dark energy is not a constant, but a dynamical field, a scalar field that changes over time and space, then it is a fifth fundamental force, modifying gravity at cosmological scales. If gravity works differently at cosmological scales than in the solar system, then every theory of structure formation, galaxy evolution, and the universe's ultimate fate needs to be rebuilt from scratch. The universe's expansion is accelerating. We don't know what is pushing it. We named it and moved on. The things we named without understanding tend to accumulate. Number 3. The X17 boson. Attila Krajna-Horke at the Hungarian Academy of Sciences Institute for Nuclear Research and Debration was not looking for a new particle in 2016. He was measuring angular correlations in electron-positron pairs emitted during nuclear transitions in beryllium-8. It was a decay spectroscopy experiment, careful nuclear physics, the kind that fills conference proceedings without making headlines. The standard model predicts that when excited beryllium-8 transitions to its ground state, it emits gamma rays and occasionally produces electron-positron pairs. The angular distribution of these pairs follows a known curve derived from quantum electrodynamics. There are no surprises in beryllium-8. It has been studied for 80 years. Krajna-Horke's team found an anomalous excess of electron-positron pairs at a separation angle of 140 degrees, not a 1 or 2 sigma fluctuation. The excess was 6.8 standard deviations. The odds of a statistical fluke at that significance are roughly 1 in 100 billion. Krajna-Horke published in Physical Review Letters in 2016. The excess was consistent with a new boson of mass 17 megaelectron volts named X17. In 2019, his team published a second paper in Physical Review Letters reporting the same anomaly in helium-4 nuclear transitions at 17.6 megaelectron volts. A different nucleus, same particle. In 2021, they reported it again in carbon-12 transitions. Jonathan Feng at UC Irvine and Bart Fornell at UC San Diego proposed in a 2016 Physical Review Letters paper that X17 could be a protophobic fifth-force boson, a particle that couples to neutrons but not protons, evading existing constraints. The counterargument? No other experiment has confirmed X17. The Padme experiment at the Frascati National Laboratory in Italy searched specifically for it in 2022 and found no signal. The dark light experiment at Jefferson Laboratory set upper limits on such a boson's coupling. The limits are tight, but have gaps at exactly the parameter space where X17 would sit. The MEG experiment at Psi in Switzerland found no evidence in a decay channel X17 should appear in. If X17 is real, if a 6.8 sigma result in 3 different nuclei is correct, it is a fifth fundamental force of nature. There are 4 known forces. Everything in your experience is built from 4 interactions. The X17 experiment suggests there may be a 5th one, and it has been sitting unnoticed in beryllium-8 for the entire history of nuclear physics. What else are we not seeing? New forces have a way of revealing old problems in a new light. Number 2. The dark photon. Holger Miller at UC Berkeley and his team were not looking for hidden sector physics in 2014. They were testing the fine structure constant, the dimensionless number that controls how strongly light interacts with matter, using atom interferometry to compare the recoil velocity of cesium atoms struck by photons. Precision metrology, the kind of measurement that takes 3 years of preparation for a single number. The standard model has 4 fundamental force carriers: photons for electromagnetism, W and Z bosons for the weak force, gluons for the strong force, and no confirmed carrier for gravity at the quantum level. Extensions to the standard model, including kinetic mixing models first proposed by Bob Holdham at the University of Toronto in 1986, published in Physics Letters B. Predict a dark photon, a new boson from a hidden U1 gauge symmetry that mixes with ordinary photons. It would be invisible to direct detection, but would leave traces in precision electroweak measurements. When Mellor's team published their fine structure constant measurement in Physical Review Letters in 2018, they found a value of alpha Chel 1, 137.035999046. That same year, Sada Guilati Khalifa at Sorbonne University published a competing measurement using rubidium atoms, alpha Tex 1 137.035999206. The two measurements disagreed by 2.4 parts per billion, a 5.4 standard deviation discrepancy between the two most precise measurements ever made of the same constant. Muon anomalous magnetic moment provides the second data point. The G-2 experiment at Fermilab, led by Chris Pauly, published in Physical Review Letters in 2021 and updated in 2023, measured the muon's magnetic moment at 2.0023318411 times 10 to the power of weight, at a value deviating from standard model prediction by 4.2 standard deviations. Dark photons coupling differently to muons than electrons are among the candidate explanations. The ATLAS experiment at CERN searched for dark photons in 2021 in the mass range between 10 and 70 gigaelectron volts. No detection. The LHCb collaboration set tighter limits in 2022. Still no detection. The Baybar experiment at SLAC excluded large portions of dark photon parameter space. Yet the alpha discrepancy between cesium and rubidium sits unresolved in two peer-reviewed papers with no experimental error to point to. 2 labs, 2 atoms, 2 values, 1 constant. If the fine structure constant has some energy dependence that standard KED doesn't predict, and a dark photon mixing with the photon could produce exactly that, then the number controlling all of chemistry, all of atomic structure, all of light, is slightly wrong in a way we cannot currently explain. Your body is built from chemical bonds held together by alpha. How constant is it? And then there is the hypothesis that unifies all of it. Number 1. The mirror matter hypothesis. Robert Foote at the University of Melbourne was not proposing a radical alternative physics in 1991. He was working on a theoretical inconsistency and parity violation. The weak force violates parity symmetry, it distinguishes left from right, treating left-handed particles differently from right-handed ones. This was discovered by Chen-Shung Wu in 1956, published in Physical Review. Foote's question was philosophical before it was physical. If the laws of physics violate parity, why does the universe still exist in a consistent mathematical framework? His answer, developed with Volkis and Joshi at Melbourne and published in Physics Letters B in 1991, was that parity could be restored if every particle in the standard model has a mirror partner, a shadow particle with opposite parity, interacting via a mirror copy of all 4 fundamental forces. The standard model's particle content is not predicted by the theory. It is observed and inserted. There is no theoretical reason why the electron should exist, but a mirror electron should not. The standard model is silent on this. Mirror matter would not interact with ordinary matter through electromagnetism, the weak force, or the strong force, only through gravity and through a tiny kinetic mixing term between ordinary photons and mirror photons. It would be, functionally, dark matter. Foote published a comprehensive analysis in the International Journal of Modern Physics A in 2004, showing that mirror matter models predict galaxy rotation curves, cluster mass distributions, and the CMB power spectrum consistent with current data, without requiring a new dark matter particle, only existing standard model particles in a mirror sector. The model naturally explains why dark matter clumps like ordinary matter has its own mirror gravity, mirror electromagnetism, and mirror structure formation. Traditional dark matter particles, WIMPs, axions, clump far less efficiently.